Welcome to Hidden Layers, where we explore the people and the technology behind artificial intelligence. I'm your host, Ron Green. AI is advancing rapidly these days, with groundbreaking announcements being made seemingly weekly. Much of this is driven by scale, with large models trained on vast data sets becoming the norm. A critical component enabling this growth is high-performance computing, or HPC. Large AI models require immense amount of computational power and sophisticated infrastructure. A recent example is Llama 3, Meta's newest large language model, which was trained on over 20,000 GPUs. Managing computer resources at this scale is incredibly complex, and that's where HPC comes in. Today, we're going behind the scenes of high-performance computing, and I'm joined by two experts, Jay Boisseau and Luke Wilson. Together, we're going to explore how high-performance computing is enabling AI to make groundbreaking progress. Jay is CEO of Visius, a consultancy for strategic planning, solutions design, and training in high-performance computing, artificial intelligence, and advanced computing. He's also the founder and executive director of the Austin Forum on Technology and Society. Recently, Jay launched the Austin AI Alliance, a consortium promoting AI advancement and responsible use. He holds a doctorate in astronomy from UT Austin and an undergraduate degree in astronomy and physics from the University of Virginia. Luke is chief data scientist at Visius and a high-performance computing and AI innovator with over 20 years of experience. He's published over 24 research papers and holds nearly 50 patents. Notably, he supported data processing for the Nobel Prize-winning LIGO project and optimized early transformer neural networks. Luke earned his PhD in computer science from the University of Texas at San Antonio and bachelor's and master's degrees from Texas A&M University, Corpus Christi. Jay, Luke, welcome.
Thank you, Ron.
All right, so high-performance computing, really, really important. It's kind of an unsung hero within AI. You also have both incredibly fascinating backgrounds. I'd love to know a little bit before we kick off, like how you got involved. Like, Jay, how did you get involved in the first place?
When I was at the University of Virginia, I couldn't make up my mind between astronomy and physics and computing. And computing was, of course, relatively new as an academic discipline then. So I did a double major in astronomy and physics, and I just took a bunch of computing classes. I guess it would have been a minor had they had such a minor back then. And back in those days, computing was taught as a service department for the science and engineering departments. There was computer science as its own discipline, and especially to graduate people for the dot-com world, didn't really exist back in the, 80s, we'll say. So there was no .com yet. So really computing was really about helping people do math and science. And that's what really got me into it. It got me fascinated. These were powerful tools for solving physics equations. And astronomy, of course, is physics applied to the cosmos. So I went to graduate school in astronomy and continued to take physics and computing classes at UT because I still, even though I'd already picked my dissertation degree program, was fascinated by other branches of physics and by computing overall. And that's what really got me into supercomputing. To do any really big problem, to do the simulation science needed to solve it, you need a supercomputer of some type. And in those days, it was Cray supercomputers. And that's what got me into supercomputing. And instead of applying for astronomy jobs, I applied for computing jobs at places that supported astronomy so that I could be more general in the use of supercomputing.
I'm really jealous. I always wanted to have access and use a Cray computer. That would have been a dream about 30 years ago. Love it.
That's about right.
Luke, how about you?
So, in the same way that Jay kind of stumbled into high-performance computing by accident, I kind of did the same thing, except not from a scientific computing background. So I was a graduate student at Texas A&M University, Corpus Christi. I was working on building genetic algorithms. So from an AI background, kind of in the very beginning, building these genetic algorithm-based systems for moving the robot arm on the International Space Station, finding a way to optimize it so that the astronauts didn't have to move it around themselves. And we discovered that we just couldn't build a large enough evolutionary system on a single computer. And so we had to, build a cluster, learn how to program it, and do all that. So that's kind of how I started in high-performance computing, is parallelizing AI. And here we are 20 years later doing it again.
Wow. All right. Well, I love that I love that work on genetic algorithms. We might have to have a separate episode where we dig into that a little bit. That's another one of my passions. Okay, so let's jump into high performance computing. So this is a field that a lot of people in AI don't know about. Most AI researchers sort of set a few levels above this, right? They're thinking about the algorithms, they're thinking about the architectures, and they're just assuming that all of the compute and flow and data will happen and it will be reliable. So HPC systems differ from traditional computer systems in many, many ways. Let's start there. Jay, can you kind of walk us through kind of the main ways they differ?
Sure. And I'll go back to the Cray part that I mentioned in my graduate work. In the history of computing, the term supercomputer was first invented for the class of computers that were much more powerful, much more expensive, but much more powerful than all of the mainstream computers. So in the early days of supercomputing, you kind of didn't need to define a supercomputer. You knew it when you saw it. It had a logo like Cray or CDC or something on the side. And it was just, It was fundamentally different the way the architecture was built, proprietary designs, proprietary software, incredibly expensive budgets to build them. You would never do email on them or things like that. They were purpose built for very large problems. Then, of course, what happened, we saw the 80s and 90s start to lead to things like PCs and commoditized processors and commoditized memory. And so people started figuring out in the 90s, led by Don Becker and Thomas Sterling, that you could lash together some of these commodity PCs and workstations and kind of make a supercomputer that way. It was very much a virtual supercomputer, not virtualized at the software level, but kind of a virtual logical supercomputer, only it wasn't really. It was a bunch of different address spaces, different memory, different processors that you were making work together at the system software layer and the applications software layer. Nonetheless, if you did both of those things right, you could make it combine the performance and memory of the set of computers. And so supercomputing went from being proprietary, purpose-built systems that were special to scale-out clusters of commodity systems. And that architecture won because of economies of scale and price performance and how all that's played out. They are definitely harder to program now. Today's HPC systems, and the word supercomputing is kind of making a comeback lately for the very large HPC clusters. But model has won, and the major augmentation, of course, has been the addition of GPUs to this. GPUs not even for the G anymore. They don't really do graphics on the large clusters for AI anymore. They just do extra compute with even higher price performance. And so that is what HPC is now. So the same technologies you can get in your laptop and desktop are very similar to the technologies in today's HPC systems, all the way up to the largest ones in the world. Yes, they're enterprise higher end versions of the processors and GPUs, and the network is usually a very high end network with low latency and high bandwidth. But basically the technology stack looks commodity at the very high end and then is integrated and scaled in a way that if the application developer also does their job, they can make it work like a single, very powerful computer.
I want to double tap on that just a little bit. Is the reason this sort of clustered approach to supercomputing, is the reason that won out is simply that you can incrementally scale it. And so you're not buying one big supercomputer, and then if you want to double power, you need to buy another one? Or are there other more kind of nuanced factors to it, do you think?
Couple of reasons it went out. One, it was all open source at the beginning. And so academics and lab folks really got into this open source, being able to see the software. And people published a lot of papers on how to build clusters. And, scientists, as many papers as they can publish, they like. So some were on what they did with the cluster, but some were just on how they built the cluster and did software and such. But you're right. It scaled down as well as up. In fact, it didn't scale up very far in the 90s and early 2000s. But they scaled down. So an academic lab could link together 4, 8, 16 workstations, and it was way less expensive than a $20 million Cray. So it made it approachable to have more powerful computers albeit maybe not Cray level in the early days, but much cheaper and much more accessible to have them. Now, of course, the scaling goes all the way to the other end as well. So we've been able to scale these clusters to tens of thousands of nodes. And so it both enables you to scale down to 2 computers can be a cluster. So just twice as much as one, but you can also scale to 20,000 nodes in that cluster as well.
Okay. So that's a perfect segue, because once you get clusters large enough, a whole new set of problems arise. So if you're dealing with a supercomputer, like let's say a Cray from 30 years ago, you might have one memory space, right? Everything's local. You're not worrying about a lot of the complexities that come up with today's HPC. So let's talk about some of those. So I know we've got scheduling, right? You're scheduling out compute. You've got all these different boxes on the network. You've got distributed file systems. You've got redundancy and fault tolerance. And one of the big issues is power and climate. Let's just kind of take these one at a time, Luke. Scheduling, that is a famously difficult problem, right? I think it's actually MP complete in the sense that it's unsolvable in polynomial time. Is that one of the chief problems associated with HPC?
So, you're right. There's a lot of research that's gone into scheduling over the last 30 to 40 years. It is an NP-complete problem. But in terms of the way that we do scheduling for high-performance systems, we really look back to the days of the supercomputers and the mainframes for how we do it. It's a time-sliced based system. Originally, it was scheduling so that 2 people didn't overrun the same memory address space at the same time. But now it's both for time slicing and for resource slicing. So we have this process where we're taking a very pared down scheduling problem. We're not doing this at an academic level. It's not the NP complete problem. It's a pseudo polynomial problem at this point, where you're saying I have a fixed number of resources, I have a number of jobs I want to fill, and we're doing a bin packing problem within a time window in order to most efficiently pack as many jobs as possible onto the resources we have. And that's just for cost and efficiency purposes, right? We want to be sure that we're using as much of the system as possible at any given time, so that, one, people are getting their work done. It's inefficient to just leave people hanging in queue and waiting for days and weeks on end before their job runs. But also, these systems are really expensive to run. They take an enormous amount of power, and being able to use even a very simple scheduling technique with a package like Slurm, or IBM used to have a package called Load Leveler that was kind of used for scheduling IBM systems, but Slurm is kind of the predominant one nowadays. Came out of Lawrence Livermore National Labs, started out as an open source project like many of the modern HPC software stacks, and is the de facto standard today, really to make sure that we're not wasting the resources on these really expensive systems.
Right. I was going to ask you, is Slurm the default that you go for these days?
Well, there's a couple of different ways you can go. So Slurm, for those systems that are really still very traditional HPC with very traditional kind of simulation and modeling users that are used to that batch scheduled system, Slurm works really well. Okay. For a lot of these modern AI clusters that are being built to run these large language models and transformer models and things like that, we tend to see more Kubernetes being used for this. And we've seen a lot of kind of lessons learned from the high performance computing community brought into Kubernetes, because when Kubernetes first came out, it was really just for kind of container drop, persistent services. If something dies, we can move that pod to a different resource or something like that. But now there are all these open source projects again. Gotta love the open source software community. These open source software projects that are bringing the capabilities of batch scheduled HPC systems to Kubernetes.
Okay, I didn't know that. Yeah. Okay, I was going to ask later about how Kubernetes fit into this world, because it's one of the dominant orchestration tools. Okay, what about the distributed data problem here? I mean, that's just completely orthogonal and as complicated.
Yeah, file systems have always been kind of the Achilles heel of these clustered high-performance computing systems. I mean, it's one thing to get a bunch of computers together and then network them together, but being able to read and write data in and out of files has been enormously difficult. And there are so many, efforts in the distributed file system graveyard that have kind of come and gone over the years. Right now, I would say one of the leading distributed I won't say distributed file system, I'll say parallel file system, because there's a different set of requirements for a distributed file system than there is for a parallel file system. So on large HPC systems, parallel file systems where you have multiple processes on multiple servers reading and writing from the same file, the same inode, is a very common technique. And so they have to have ways of striping and spreading the content of this one inode across multiple disks, multiple RAID arrays, multiple servers. And so parallel file systems like Lustre are, Lustre itself is really probably the predominant parallel file system in the market right now. And it's designed for that type of workflow where you have thousands of processes writing into the same file at the same time.
Okay, and that's a perfect segue again into redundancy and fault tolerance. And that obviously includes not just sort of file system and data redundancy, but now what about a node goes offline or you have networking failures? How are those types of difficulties handled at scale in HPC today?
Well, and this is an area, fault tolerance and redundancy has been an active area of research for decades. And the reason it's been such an active area of research is because it's so difficult, especially in the way we program large HPC systems and the way we write parallelized applications. Most of these applications, especially for simulation modeling, less so for like AI workloads and like neural network training, things like that. But for these modeling and simulation workloads, they're very tightly coupled. So, a process running on server A is dependent on receiving a message from a process running on server B, and it has to happen in a certain order. And if it doesn't get the message, it can't go back and ask for that message to be sent again. And so everything has to be working all the time or the whole system falls over. And so redundancy, especially in these large parallel applications, has always been a problem. If you lose one process, you're really just stuck restarting the process from a last known good state if you happen to have a checkpoint file or something like that.
Okay. And the last point I wanted to cover on this, and Jay, I'll ask you about this, is sort of power consumption. It's pretty well known, I think, by everybody now that these really, really large AI systems are obscenely power hungry. And, there are climate issues and all of that. How is HPC addressing that, thinking about that these days?
Well, first we should, make sure and level set here, which is that it's not that computers are getting less efficient. Processors are more efficient than they've ever been, right? More performance per watt than ever. But we're asking for more performance than ever per processor. So the watts are going to go up. And then we're linking more of them together to do these very large models. So the watts go way up. So now we have supercomputers in the world that use 5, 10, 20 megawatts of power, including the ones to solve the great big simulation problems, like the computer at Oak Ridge National Lab has been number one in the world for quite a while. And it was primarily designed for simulation problems, but it also, now that we are in the era of big data, can solve big data analytics problems. And because it's got GPU technology in it, it can also do AI problems for which GPUs happen to be very good accelerators for the performance characteristics in those algorithms. So it's a pretty general purpose supercomputer, but it is a 20 megawatt supercomputer. So it can do more than ever, and it can do more per watt than ever, but we just ask for a lot from these things. Yeah. And these big LLM models, of course, training those requires a staggering amount. Going back to simulation though, we still can't build supercomputers big enough to accurately solve with direct numerical simulation most of the interesting problems in nature we want to solve. So we're just doing approximations. So we always want bigger supercomputers. So it's not just AI's fault. It's it's nature's fault in some way. Nature's working in parallel. And if you want to simulate it, you need a massive parallel computer that essentially can code all of nature into it. We're not going to get that. All that being said, so the power problem is, it's justified because of the importance of the problems. But I think the big distinction should be made is it a real-time problem or is it a batch problem? Is it something that maybe doesn't have to be run in real time in a specific location? Then you want to build your data centers in places where power is cheap, which every CEO and their CFO agrees with, but you should also build them where power is green. And so what I hope that we will see is more and more of these data centers that are training large AI models as well as the ones that are doing large research simulations in places where the power comes from hydroelectric and solar and wind. And true, not all renewables are 24/7, 365. Although, as we know here in Texas, wind is now in West Texas cheaper than carbon-based power 95% of the time. So if you don't have a real uptime requirement, cheaper power can be a real attractive thing. And we're starting to see that, right? First, the Bitcoin miners started moving their mining facilities to where the power was cheap and they were willing to be down for a little bit because there was no real-time requirement. Right. I hope we see this with training some of the large AI models as well. Better for the world that way. And it is absolutely true that data center power is growing. It's a growing percentage of all power. So we really should be cognizant of where the power is coming from. There's a lot of work around making the data centers more efficient, but that's just playing with 5 or 10% efficiency as opposed to 100% of baseline power being green. And that's one of the things that the HPC community cares about, and the AI subset of that community, who often don't realize they're HPCers, but they are. They're using an HPC system.
Absolutely.
They seem to be aware of the carbon impact, but the market is so competitive right now. It does a lot of times see, yeah, we should solve that problem sometime, but we need to get GPT-4
We've got to get this new model out quickly.
Yeah.
So one of the things that makes, sort of modern AI systems amenable to being trained on like the Llama model 20,000 plus GPUs is that the core operation is matrix multiplication, which itself is a really great candidate for being distributed and done in parallel. Luke, you've done work on optimizing the transformer architecture, which is the dominant deep learning architecture. It's a go-to architecture behind pretty much all of the generative models and large language models and DALL-E and those types of things we see out there today. Tell us about that. That's just fascinating.
Yeah, it's amazing how much similarity there is between the work that's going on in the AI space and the work that has happened over the last 20, 30 years in high-performance computing in the simulation and modeling space. And because these two communities don't really talk to one another, they're not sharing a lot of the lessons learned. And so you're absolutely right. We look at these large neural networks and the process of doing backpropagation when you've structured your neural network as a connectivity matrix is really the same as solving a partial differential equation. Right. And so now being able to take those lessons we've learned over years of kind of painful trial and error in the simulation and modeling space and apply them into AI is something I've been really passionate about. And so after Google released Attention Is All You Need in 2017, we started looking at this transformer architecture and some of these earlier models, kind of early BERT and some of these other transformer approaches. And we were looking at the way that the layers were structured. We were looking specifically at embedding layers. So these embedding layers are really interesting in that, we see these large embedding layers getting larger and larger and larger to handle larger and larger token windows. But when they were first built, the assumption was that these embeddings should be sparse. Right? Because the assumption was, there's not going to be an enormous amount of information stored in the whole idea is we're doing some information reduction, we're doing some information compression into the embedding layer. And from a pure CS kind of theoretical perspective, that makes a lot of sense. Because you say, I'm making it space efficient, I'm making it time efficient. But what happens on a real computer is that you end up doing 2 lookups per index for every element in an embedding array, right? Because you have to look up the index and then you have to do a pointer chase, right? And then you're looking up the data point inside the embedding. And this is really bad for computers because this is not the way that processors are built. Processors are designed to move entire chunks of data around one cache line at a time. And so we started exploring the idea of building these as dense matrices, these embedding layers as dense matrices as opposed to sparse matrices. And what we found is we can improve their performance by 8 to 10 to 14x.
Wow.
And improve their time to solution by 20 times. So the lookup time goes way down, the performance goes way up, the space used goes down because now instead of needing 2 elements for every single entry, you only need 1 because everything is naturally indexed. And so being able to apply these HPC lessons, lessons about the way processors work, the way networks move data around, the way things are encoded in RAM, encoded in register, encoded in cache, and applying that to these kind of upper level concepts that are happening in the neural network. It was really the step that needed to happen in order to make these a highly parallelizable process. And now we're training on tens of thousands of GPUs at a time, moving data around the network because we're finally applying all the techniques we've learned in the simulation and modeling space to the numerical application of these AI systems.
I always think about HPC systems as like managing almost like a living organism. It's like a creature, and there are going to be unexpected behaviors. What are the most difficult challenges right now with managing a really large HPC system?
I mean, cost is one of them, right? Just because the demand for ever larger ones has gone up. And so the percentage of your OpEx budget that was power in the old days was, less than 10%. You were basically paying people to run it, to program it, to provide user support, et cetera. Now the OpEx budget has such a huge power component that puts a strain on the overall budget, right? Because you still need people to run it and program it and support it and maintain it and all of this. But now you need a very large power budget as well. So that's one. But as we talked about earlier in the podcast, fault tolerance is one. As you build a system, and these really are systems of systems, right? You sort of alluded to that in your opening question. Each individual component, server in it is a system, but its aggregate properties are a bit different as a system of systems. On the failure mode, though, from a strict hardware perspective, you can figure out what your failure rates are going to be by the failure rates of any one component. And then you have a certain, n components in it. And so that increases your chance of a failure. Plus, they're now packed very densely, too, in very hot racks as well. So not standalone components and nice, cool data centers. They're in very hot racks and hot data centers. And, we do a lot to cool these things down to the minimum needed to keep the operating environment good enough to keep them reliable, but you're going to have some failures there.
Well, I'm kind of curious on the point. Like if somebody said, "Oh, we had a failure," and you just said, "I'm going to make a wild guess," it's probably what? What is the likely failure? Most common.
DIMMs still are a source of failure. Power supplies are a source of failure.
Okay.
Processors generally not so much. You don't really see problems there, but it's usually something like a DIMM.
Okay.
If it's if you're using disk-based parallel file system, a disconnect. Now, a lot of these errors are corrected, right? Error correcting memory, RAID at the disk level, et cetera. So errors happen all the time that aren't failures. They're corrected errors.
Right.
But in terms of failures, components do fail throughout that commodity technology-based stack. And if you've written a large parallel simulation application, you better have checkpointed the application every so often because it's going to bring the whole application down. And hopefully not after running for 8, 16, 24, 2 days, 3 days, 4 days, something like that. Hopefully you've checkpointed it every several hours so that you never lose more than 8 or 10 hours worth of 10,000 nodes of compute or something like that.
Okay.
Something that's really fun about these very large systems, though, is, and everyone who's been in AI for a long time understands this whole concept of emergent behavior. You will see errors pop up at 10,000 nodes or 100,000 processes or 100 or a million cores that don't pop up at smaller scales. And so HPC is a lot about, especially at the kind of support and repair level, figuring out what these emergent behaviors are going to be, because you see all these problems that happen at scale that never happened before. And when Jay and I both dealt with this sort of problem from users in the past, where it's like, well, I never had this problem before when I was running on 32 cores, or I was running on 128 nodes or something like that. But now I'm running at 1,000 and all of a sudden I'm having these problems. Like, well, you just weren't large enough yet to see these behaviors show up. And so, these are really hard problems to diagnose. And so, whereas a lot of the times I can say, oh, you probably had a file system problem, you probably had a memory DIMM failure or something like that. Sometimes, especially in the software, seeing these emergent problems pop up is is one of the hurdles that we have to get over.
Right. It's one of the reasons I always think about HPC systems is like living organisms. And as they scale, sometimes you'll have maybe software bugs that only manifest themselves at some certain scale. And it's that emergent behavior you see.
Well, the bigger problem, though, of course, is scaling itself, right? Everybody, when you first hear about HPC and you hear, they put 1,000 nodes into that into that supercomputer, 1,000 different servers in it. The codes are 1,000 times faster, right? And the reality is scaling itself is the hard part, right? So, most HPC system sizes, most users aren't going to deal with failures very often. The center might deal with failures over all the users, over all the hours of the days and days of the year but individual users probably won't see that much. But what they'll see every time they try to run their code on more nodes is they'll see performance reduced over what they hoped it would be, because it doesn't scale linearly. You're having to move data around across a network in between the computations, and you want the computations to scale linearly, but time spent communicating is not time spent computing. And
is there, it's not a linear scale, and there's overhead as you grow with the number of nodes, but is there a general scale at which you can expect it, or does that scale bend at different points?
Completely depends on how much of the time in your application is spent in parallel computation versus spent in anything else, serial computation, I/O, communications between nodes to do updates so you can get to the next round of computation.
Any of those bottlenecks just drops
any
down.
of those. And then the hardware influences how much time it spends in those other non-compute things. A slow network takes longer to share data from Go cells in a simulation problem or whatever to all the other nodes so you can start computing again. A parallel file system with fewer disk drives takes longer to finish that writing of that parallel file to all of the drives than a larger parallel file system. So the hardware can impact it, the choice of algorithm can impact it. And sometimes there's even some things that go backwards, like you can find an algorithm that's very, very efficient and scales very well, and you pat yourself on the back because you say, well, I got scalability of 900 on 1,000 nodes. Oh, pat yourself on the back. That's pretty good. Then you find an algorithm that really didn't get nearly as good efficiency, but it solved the whole problem in 1/10 of the time. And then you have to remember, it's not just about efficiency. It's about getting the fastest answer to the problem you can. It's called high performance computing, not perfectly linear scalable computing.
Right.
Ultimately, software and the choice of algorithm often makes a bigger difference than even the hardware.
Right. Well, on that note, is there anything out there on the research front that you're particularly excited about, either of you?
So I think some of the most interesting research I see right now is at the intersection of simulation and modeling and artificial intelligence, where we're either coupling AI models in with direct simulation, direct numerical physics, or we're replacing direct simulation with AI. There's a lot of work going on in the computational fluid dynamics space, for example, where we're replacing forward simulations of the Navier-Stokes equations with neural ODEs, and we're doing either an ordinary differential equation or a partial differential equation approximation using a neural network as opposed to using direct simulation.
Well,
we're getting good enough answers in fractions of the time.
Right. And I think of on that front, if you watch some of the videos from Sora, and you can watch how it will simulate liquids and interactions between different bodies, and none of that was programmed. It had to pick up and learn these sort of compressed, physics simulation capabilities, and that's very in line with what you're talking about, I assume.
Yeah, one of the most recent innovations in this space is the concept of the physics-informed neural network. So it's using kind of the general rules, the fundamental laws of physics as part of its internal understanding.
Yeah.
But it's doing an approximation based on that understanding of the fundamental laws of nature in order to make its forward approximations. And so now we're getting very high fidelity approximations of physical systems in fractions of the time. And it's not only good for these forward simulations, for these direct simulations, doing indirect simulations where we're trying to do uncertainty reduction, we're trying to do ensembles of direct simulations where we have uncertainty in the system, like in weather forecasting and things like that. This allows us to get high fidelity responses at fractions of the time. Better forecasts, better airplanes, better cars, all those sorts of things that happen when you do like fluid dynamic simulations.
We did an episode a few months ago on protein folding, and some of the new models, especially like AlphaFold 2 and 3, can solve some of these protein folding problems in minutes that used to take, years of research. I wanted to ask about if somebody's interested in getting to HPC. Both of you took the traditional route, which is there is no route. You just kind of wind it up randomly. If you were interested and you wanted to go study and get involved in this, any recommendations on sources or paths?
Yeah, there really isn't a common traditional route to it. There's not a degree in high performance computing, for example. But high performance computing has been around for decades because it's critical in solving large scale problems. So most universities have a high performance computing center. So whatever your major, Luke went one route, computer science. I went natural science route as an end user of these systems as opposed to a maker. We both ended up in HPC. So there's multiple ways people get attracted to using these big, powerful systems. And most universities, while not having a degree program in it, they have a high-performance computing cluster or many clusters. There's also lots of good online materials. People have written some very good books on this topic as well. So it's not one where you're going to find tons of YouTube videos that help you do it like you do in AI, but there's some out there. But especially at the university scale, there's a lot of, including, of course, here, the best academic supercomputing center in the world is the one we used to work at, the Texas Advanced Computing Center. So anyone at UT has a great opportunity to, and they teach classes and workshops, have jobs for students, et cetera. But pretty much any university you go to these days, and if you're partnering with a lab in anything, they certainly have it. Most companies now that are, especially if they're doing science and engineering, but also if they're doing large-scale data analytics, financial services companies, for example, have very large HPC systems. Oil and gas companies have very large HPC systems. So if you're working for a movie theater chain, maybe you don't have access to HPC. But if you're working for anyone doing science or engineering of any type, doing very large data analysis, including, retail companies like Walmart has tremendously large HPC systems. I think I can say that in this podcast. Yeah, I'm sure I can say that. So financial services companies, although now I won't say any names, but have very large ones. So you probably have, through a university space or through many jobs, not all, but many, have the ability to go cozy up to somebody in that space and ask them questions. And that's often how people get into it. And then they take, they ask more questions, they take a class, they see if they can sort of twist their job in some way to use it for some project or something. And it turns out they're very powerful and useful tools. So most people can find a way in for most jobs or academic programs.
Yeah, high performance computing really is the speakeasy of scientific professions. It's about knowing how to ask, because no one's going to have an HPC program directly. You're going to be looking for something like scientific computing or data analytics, or you're going to go through the engineering department, through the aerospace program, or through the chemical engineering department or something like that. You're going to find it somewhere else, because high performance computing is less about the tools used to create it and more about the applications that it enables. And so when you're wanting to learn about it, you're going to learn about it through the applications that it enables, and not through directly saying, I want to build clusters. You're gonna go into a discipline first, whether that's computer science or whether that's aerospace or data science or whatever it is, and then you're going to learn about it.
Okay, thank you guys so much, Jay, Luke. As an practicing AI guy, we rely upon the work and the accomplishments that you guys have brought to the table over the last few decades. And I speak for all of us in AI that we are very grateful that we're able to scale up because of the hard work that you've put in over the years. Thank you for being here today.
Thank you, Ron.
Happy to do it.
Thank you for listening to Hidden Layers. This series is hosted by Kung Fu AI, a management consulting and engineering firm focused exclusively on artificial intelligence. If you have any questions or thoughts about today's episode, or if you know someone we should feature, please visit us at kungfu.ai.